Hello, Year 10. Today we're looking at waves and how we describe the actual characteristics of the wave, as well as explaining how frequency is related to wavelength and calculating wave speed using both frequency and wavelength. As per usual, if you want to follow this lesson with the online textbook, please use pages 138 in the Physics Trilogy book to support today's lesson. So that's pages 138 to 139. So just a quick quiz, 1 to 10 in your margin. Just pause the slide now and answer the following quick questions for me. So number 1, what is the scientific word for one complete wave? We call that an oscillation. Number 2, true or false? Mechanical wave is any type of wave that travels through a medium. That's true. True or false? An electromagnetic wave travels at the speed of light when no medium is needed. That's also true. Showed you the answers there before the question. But what is the scientific definition of a transverse wave? And this is that perpendicular word again. The oscillations of a transverse wave are perpendicular to the direction in which the waves transfer energy. So how you would describe that wave as movement in a longitudinal wave, the oscillations are parallel to the direction in which the waves transfer energy. 2 waves you can describe as sound wave, mechanical and longitudinal waves. What wave is a type of wave is a light wave? It's an electromagnetic transverse or transverse. Then a bit of revision from forces in balance, which is the scalar quantity, distance or displacement, and that would be distance. Revision for BE8, photosynthesis. What is the name of the pigment that captures light for photosynthesis? Chlorophyll. If you've written chloroplast, you're halfway there, so good try. Okay, give yourself half a mark. Revision of C8, reaction rates. Name 4 ways in which the reaction can be increased. See how many you get. Use a catalyst, increase the temperature, increase the concentration, increase the surface area. Okay? So types of wave. So we've got our transverse and we've got our longitudinal. And remember that when we're looking at transverse, we're looking at the upward and downward motion as well as the moving of the energy transfer. Okay, if you didn't catch yesterday's lesson, if IT ever upload it, then we'll see. Okay, you need to know that oscillations of a transverse wave are perpendicular to the direction in which the waves transfer energy. Okay. Now those longitudinal waves, we're thinking about compression. So sound waves are a typical example of a longitudinal wave. Also seismic waves. We call those areas of compression rarefactions. And again, as I said yesterday, it's really important that we think about those and we get that spelling completely right because it's so close to so many of the other key words. And you need to know that oscillations of a longitudinal wave are parallel to the direction in which they transfer energy. If you haven't got those need to know bits in red down in your own notes, please pause the slide now and make some notes. So using waves. So waves are really important for 2 reasons. Firstly, we think about them in transferring energy, and secondly, they transfer information. So we use waves all the time. Your phone uses waves, your TV uses waves. All of those things require a wave to be effectively moving from one place to another. So these are the 5 examples that you could have had, and these are the 5 examples that you need to know. So first of all, we've got radio waves. Now, if we're talking about analog radio, that's where you sort of scan through and you find a radio station, and it can be a little bit crackly. The stronger the signal, the more closer you are to the true wavelength, the clearer the sound is. Microwaves, we talk about these transmitting mobile phone signals, but don't remember these are exactly the same microwaves as we use for heating food. Light waves down a fibre optic cable. That is lovely. That's how we get our broadband, a lot of us, into our homes. Also, those light waves down fibre optic cables also are those lovely Christmas trees that you have that are sort of all change colours and at Christmas. That's when you get Christmas trees. Christmas. Okay, sound waves so that we can hear, and infrared waves or infrared wave radiation in remote controls. So there are lots and lots of other examples, but there's some good examples there that it'd be good to jot down, maybe make a nice mind map of how they're all linking together and where they could be used. To be able to transfer the information effectively, they need to know how much energy and how fast it can be transferred, and that's where the maths comes into this. So we're going to use the properties of the wave to give you the information you need, and in order to do that, you need to know the anatomy of your wave. So pause the slide and sketch this diagram and make sure that you label it really accurately. Okay? Right. So the amplitude, okay, is the point at which it's of displacement. That's the maximum point at which it is displaced from zero. So that dotted line we've got horizontal across the middle of the screen is 0. And we measure that in meters. We might use micrometers, okay, but when we're calculating this, we always need to convert back to meters. Wavelength, and that funny sign there is called lambda. Wavelength is the length of one complete wave. Now you can measure that from peak to peak of your wave, or trough to trough to your wave, or the 0 here to the 0 here. It really doesn't matter where you do that on the graph paper, in a test, or in a practice question, as long as you make sure that you're calculating only one wavelength and you're doing it consistently across the page if you're counting multiple wavelengths. Okay? And again, wavelengths is measured in meters. The peak is the highest point of the wave. The trough is the lowest point of the wave. Undisturbed is the centre line of the wave, or sometimes referred to as 0 or origin. So let's look at comparing the properties of my transverse and longitudinal wave. So the top diagram, as it says, is for a transverse wave, and we've already talked about wavelength, and we've talked about displacement, and the bottom graph, bottom spring, I keep calling it graph, is looking specifically at how we would measure those in a longitudinal wave. If I look at the top graph here, this piece here, okay, this section here, this is the displacement, that's my amplitude, this is my wavelength, and we can see a nice clear wave. However, displacement can be easily measured along the scale, along the y-axis, and the distance can easily be measured along the x-axis. This trace here is called an oscilloscope trace. Now when we're looking at it in a spring, we get this different pattern. We get these sections of compression, okay, and we get these sections of rarefaction. And the rarefaction is where the spring is stretching outwards, recoiling, just before it recoils, and the air displacement can move back in both directions. Now, clearly, some of you may have seen one of these and some of you may not. Okay, so the machine we use here to convert longitudinal waves into transverse waves, making them much easier to see and measure, is called an oscilloscope. And it looks like a very old television, and all it really does is have one colour on it, which is like a light bluey colour. And you will have seen these back in year 7 and year 8. when you get back into school, we will ensure that you get the opportunity to see how one of these works. It's riveting. So just quickly, knowledge check, sketch a wave out, or just write A, B, C, D, E and label them for me. Pause the slide. So here comes the answers. How did you do? Give yourself a score. Are you awesome? Are you struggling? Don't panic. I'll add a link to Bite Size so that you can check up on anything that you need to go over after this. So calculating wave frequency. So frequency is the number of complete waves passing a fixed point in a second. And again, we've talked about the fact that it's a complete wave. Now we can either again measure from peak to peak, trough to trough, or from the zero, the flat line in the middle. Okay. Frequency of the wave on the top diagram. So we need to look at this is 5 Hertz. And I can see, why have we got 5 Hertz? The period of the wave is taken, time taken to complete past one fixed point. The period is measured in seconds. So the period in seconds is 1 divided by the frequency. Now you need to remember this equation. Right, here we go. So when we're working out, wave speed is the speed at which the energy is transferred by a wave. So wave speed is equal to frequency times wavelength. Now remember, you can pop that one into a triangle and that would be expected to be rearranged, especially for the height here. So wave period is t, which is the time it takes to pass through a point in seconds. Period equals 1 divided by frequency. So the wave opposite has a frequency of 0.5 Hertz and a wavelength of 6 centimeters. We need to convert that 6 centimeters into meters, and we need to calculate the wave period and the wave speed. To do this, we need to do 1 divided by 0.5, gives me 2 seconds. Therefore, the wave speed is 0.5 times 0.06, gives me a speed of 0.03 meters per second. Got my notes all mixed up. Oh dear. So, a bit of practice for you. Have a go at doing these. Pause the slide now. Using the equation, you can need a calculator. So calculate the wave speed. If the wavelength is 12 meters and the frequency is 20 Hertz, 20 times 12 equals 240 meters per second. Calculate the wave speed if the wavelength is 12 meters and the frequency is 1000 Hertz. And it says here, give your answer in standard form. So 1000 times 12 equals 12,000 meters per second. That's a bit of a large number, so we go to 1.2 times 10 to the 4 meters per second. Hopefully you all know how to do standard form. Calculate the wavelength if the wave speed is 50 meters per second and the frequency is 10 Hertz. Calculate the waves travel at the speed of light. 3 times 10 to the 8. Calculate the wavelength of an electromagnetic wave with a frequency of 200 Hertz. Ooh. So we need to rearrange the equation, and therefore we do 3 times 10 to the power of 8 divided by 200 gives me 1500 meters, which is 1.5 times 10 to the 6 meters. Calculate the period of a wave when the frequency is 60 Hertz. 1 divided by 60 equals 0.016 seconds. Hopefully that's pretty straightforward. So measuring the speed of waves in air. Now this can be really difficult to do, so we're going to look at 2 methods of doing this. First of all, we can use a stopwatch. okay? And we can then calculate the sound once it gets to a certain distance. We need quite a large distance because obviously sound travels very, very fast, and we need to factor in human reaction time. The next one is that you can use sound from a loudspeaker passes 2 microphones a set distance apart. We'll be doing this in the lab, and it's really interesting to do because actually it's quite noticeable the difference at which the sound wave passes the 2 microphones. We can also use something called a ripple tank to measure water waves. Now this is a required practical, and therefore it's something you're expected to be able to explain how to do in the exams and have had some sort of practical experience of how to do this. So a ripple tank is used to make waves which are seen under a glass tank. You can see under my glass tank I've got this shadow. So we usually put a nice sheet of white paper there to give us a nice crisp shadow. And at the top we have a strobe light, and that strobe light projects through the water, and we have this big long wooden block that has a motor on it. So the motor vibrates, and we can change the vibrations on the motor to change the ripples that it produces in our tank. So when the water ripples, produces small waves, when the peak of the wave, the water is at its thickest, and that gives us a shadow to appear here below. Where the trough of the wave is, that's where the water is its thinnest in a ripple tank, and that's why we get these nice light bands here. Now we can use a ruler to measure the size of those ripples, and that's because we're measuring from trough to trough. We know that's one wavelength. Exciting stuff. Okay, and this is how we could work out the frequency of the water wave. This is how we can work out the wavelength. Okay, and then we can work out the wave speed using the frequency and the wavelength. Right, so another practice question for you to do. Pause it, have a go at it, and here come the answers. And another set of questions. So pause this, and here come the answers. So the key points from today's lesson, these are in the online textbook, but if you haven't taken much away from today's lesson, please make sure you've got the key points down.